Hello and welcome to yet another video of Cornerstones of Math. Today I've got this interesting looking summation problem. When n is a natural number, we have to carry out the summation where k changes from 0 to n. The binomial coefficient, also known as combination, n choose n minus k divided by n plus 4 choose n minus k. So in the numerators, we have n choose n minus 1, n choose n minus 2, and so on, up to n choose 0. And in the denominator, we have n plus 4 choose n plus 4 choose n minus 1, n plus 4 choose n minus 2, and so on until n plus 4 choose 0. Alright, let's do this. I will show you more than one method, and what I would like to show you first is that so-called brute force, aka testing with small numbers such as 1 to 3 and so on, might actually work. First, what happens when n is equal to 1? Well, then we have the summation where k changes from 0 to just 1, and then we have 1 choose 1 minus k here, and 1 plus 4, hence 5 choose 1 minus k here. So when k equals 0, we have 1 choose 1 divided by 5 choose 1. And when k equals 1, we have 1 choose 0 divided by 5 choose 0. And if we calculate this, we obtain 6 over 5. And when n equals 2, then k changes from 0 to 2. And then we have 2 choose 2 minus k here. And 2 plus 4, hence 6 choose 2 minus k here. So we have this expression, and if we calculate this, you will obtain 7 over 5. And we can do it similarly for n equals 3. Now the summation goes from 0 to 3, and we have 3 choose 3 minus k divided by 7 choose 3 minus k. So now we have 4 terms in total, which will give the value 8 over 5. So there seems to be a pattern. Based on this observation, we can guess that for all natural numbers n, the summation in the problem gives n equals 2 must give the numerator 7, and n equals 3 must give the numerator 8. So the numerator must be n plus 5, and the denominator doesn't change, staying at a constant value of 5. So the answer must be n plus 5 over 5. However, this is merely a guess and not a mathematically rigorous proof. We have sort of guessed that the numbers increase in this manner, but how can you be so sure? But I will get to this point later. And let me show you another method to carry out the summation. Here I am going to use a certain property of binomial coefficients, making this an algebraical calculation rather than numerical calculation. Let us take a look at the first term and compare it to the second term. Notice that if we can somehow convert the binomial coefficients into n choose n minus 1 and n plus 4 choose n minus 1, then we can add it to the second term. In order to do so, let us use this property of binomial coefficients. N choose k is equal to n minus k plus 1 divided by k times n choose k minus 1. This formula reduces the k part by 1 while keeping the n part unchanged. If we apply this formula to the first term, then by writing n minus 1 here and here, we have to multiply the k value in the denominator are both n, and if k is equal to n minus k is 0, so we just have 1 here, but at the bottom, we have n plus 4 instead of n, so we also have to add 4 to the numerator in the bottom, so we have 5 here. This is the application of the formula. So if we simplify the first term, then we basically have 1 over 5 multiplied here to n choose n minus 1 divided by n plus 4 choose n minus 1. Therefore, Now we can add up these two terms. We have coefficient 1 over 5 here, and we just have 1 here. So as a result, we have n choose n minus 1 divided by n plus 4 choose n minus 1 multiplied by 6 over 5. So this was the process of adding up first two terms, and now let's do the similar thing with new first term and new second term. Basically, we want to change this n minus 1 into n minus 2. So we try to apply this formula again, so that we have n minus 2 here, and now the k value is n minus 1. So n minus k is equal to 1, so if we add 1, we have 2 here, and if we add additional 4, we have 6 here. If we simplify first term, now we have the multiplier 2 over 5 here, and if we add these two, considering that the coefficient here is 1, then we have n choose n minus 2 over n plus 4 choose n minus 2 term, now multiplied by 7 over 5. Then we have the next term, which must be n choose n minus 3 divided by n plus 4 choose n minus 3, and the remaining part. And now you can see where this is going. We use the formula again to change this into n minus 3, which gives the multiplier 3 over n minus 2 here and 7 over n minus 2 here, which gives the multiplier 3 over 5 here. And if we add these two, now we have the multiplier 8 over 5. Here, let us take a look at how the coefficients change as we reduce the number of terms. After we reduced one term for the first time, we had coefficient 6 over 5. Then after removing one additional term, we've got 7 over 5. And after removing another term, we got 8 over 5. Based on this pattern, we can kind of predict what the end result would be. After we reach the point where there is only a single term left, which must be n choose 0 divided by n plus 4 choose 0 term, then the multiplier would be, you see, 8 when n minus 3, 7 when n minus 2, 6 when n minus 1, and so on. So if the k part becomes 0, this part must be n plus 5, and the denominator stays at 5. And since this part is just 1, we obtain the result n plus 5 divided by 5. However, this too is merely a guess. I mean, as the number of terms decreases, the coefficient of the first term seemingly followed this pattern, but how can you be so sure that it stays in this pattern? Therefore, for the sake of being mathematically rigorous, I will complete the proof by using mathematical induction to prove our guess. So here's our guess, which is that for all natural numbers n, the summation given in the problem gives the result n plus 5 divided by 5. First, we need base case, that is, when n equals 1. I have already explained that n equals 1 gives this summation, which gives the value 6 over 5. This means that our guess is true for the base case. Next, we have induction hypothesis, which is that for some natural number m, the summation k from 0 to m of m choose m minus k divided by m plus 4 choose m minus k is equal to m plus 5 over 5. Then we want to prove for the case where n is equal to m plus 1, so let us consider the summation with m plus 1, where we add up m plus 1 choose m plus 1 minus k divided by m plus 5 choose m plus 1 minus k. We must somehow make use of the induction hypothesis, which contains the summation of only m plus 1 terms instead of m plus 2. Therefore, we split the summation into two parts the first part where k only changes from 0 to m, and we write the last term separately where k is equal to m plus 1, which is m plus 1 choose 0 divided by m plus 5 choose 0. Next, notice that the induction hypothesis contains m minus k, and so on, while our current summation contains m plus 1 minus k, and so on. We must convert these into expressions that are present in our induction hypothesis. Therefore, now let us use this property of binomial coefficients. N choose k equals n over k times n minus 1 choose k minus 1, which can decrease both n and k by 1. This gives... Now the binomial coefficients are changed into m choose m minus k divided by m plus 4 choose m minus k, and according to the formula, n in this case is m plus 1, and k is m plus 1 minus k, and in the denominator, n is m plus 5, and k is the same, m plus 1 minus k. And the second part just gives 1. This can be written as the summation of m choose m minus k divided by m plus 4 choose m minus k multiplied by m plus 1 divided by m plus 5, n plus 1. And this part right here equals m plus 5 over 5 by our induction hypothesis. So we have m plus 1 divided by m plus 5 times m plus 5 divided by 5 plus 1, which gives m plus 6 over 5. Therefore, our guess is true when n equals m plus 1. Therefore, our guess is true for all natural numbers n. And that's all for today's video. Thank you for watching. Please don't forget to hit that like button if you enjoyed this video, and I will see you in another video.